All right, welcome everyone to our Astronomy Club. It is Friday, April 24th, and it is a Hubble anniversary. Big Hubble anniversary. I know, it's so fancy. So today is the 30th anniversary of Hubble being launched into space on the Space Shuttle Discovery. For us Star Trek fans, that always means something nice. And yeah, so we're going to talk about some cool stuff that Hubble has shared with us. As always, any space questions are more than welcome. I will do my best to answer them. I do have material for the stuff that I am planning on talking about, but if there is something that has come up that you would like me to answer, please do not hesitate to ask. I am always happy to answer any questions we have. So first thing that I wanted to talk about, these transitions are not going to be pretty, but it works for me. So this is what we're going to do. But I did get a question about lightning in space that came up from our discussions on the episode club on Tuesday this week when we were talking about Battlestar Galactica, and we were discussing if there could be lightning storms, because they had lightning storms on the planet that they were in the gas giant. And so are there lightning storms in space, and what do they look like? And do they have any magnetic or gravitational or any other type component that we could detect? Awesome question. Hey, Brad. So the big answer to that is yes, it is possible. It's easy to see. Now, this is a sort of false image rendition, artist's rendition, that's the word, of lightning in space. But we do see it on planets in our solar system that are not our own. And it's static charge that builds up, and then you get this discharge, and you get this flash. Now, the big indicator isn't so much the light, because that's harder to see in space, because space is very big, but you can get a burst of electromagnetic radiation that comes from it. Now, when we ask, what kind of effects would it have? Is it magnetic? Is it gravitational? Is it, light? What would we see? Depending on the discharge, you could see various things. There's not really going to be a gravity effect from lightning in space. But because it's really small, and they may push out sort of dust clouds a little bit, but it's not going to actually have a gravitational effect. When we say magnetic, now it would have an electromagnetic component, and we do actually see these as radio signals that we see. And we have seen them studying Jupiter, studying some of the other gas giants. And again, it's from dust that builds up a static discharge. Now, what they actually call them are whistlers. It's kind of the phrase for these signals that we see that are lightning on other planets. The question is if we can get lightning in nebulas. It's easier to say. But could we get lightning in those? And in theory, yes, because there is dust present in clouds, in nebulae. Sorry, I know it's going to annoy someone, so I'll try to say it properly, but in nebulae in space, because there is dust present. However, the way that you have lightning is from a buildup of static, and then you get a discharge. And the clouds in a nebula are too dispersed to actually really result in any sort of significant contact between particles that would allow a discharge. So even though that would even allow static to build up, really. So even though nothing is saying that they couldn't have lightning in space, there's no physics that's limiting that from happening, other than the fact that the nebula are just too dispersed to actually have that static discharge. Because remember, it's the same thing. You can think of this mini lightning as when you get that static buildup and then you touch a doorknob and you get the spark. That's effectively what's going on, right? It's a discharge of static buildup, but you have to be close to that doorknob for that to happen. And dust particles in a nebula would not get close enough for that discharge. But on a gas giant or on other planets, you could actually get that discharge happening. And we've seen that, which is pretty cool. We have actually seen it in one planet, as far as I know, outside of our solar system. So we've seen it on Jupiter, we've seen various other planets, but there is one outside of our solar system. It's, you know, just fascinatingly called HAT P11b, and it has basically showed constant, like I said, these whistlers, these little radio blurps that you get, and it's just like this, like kind of a static. And they are able to pick that up with radio telescopes, and they did see this on this telescope. Oh, thank you for the subscription. So, yeah, I know, right? So we do see lightning in space. It doesn't have a gravity effect. It has an electromagnetic component in the sense that it gives off little radio signals that we call whistlers. So there's that question. Another question that I got is really good and interesting, and I think kind of bends our brains a little bit, that we're going to keep bending our brains as we talk about Hubble, but that has to do with Andromeda and the Milky Way. So when we've talked about, this is an artist rendition, but when we've talked about our local galaxy cluster, remember our cosmological address is our star system, and it's one star in the Milky Way galaxy. Milky Way galaxy is one galaxy in a cluster of galaxies called the local group, and then that is within our universe. In our local group, we have the Milky Way, which we see as a line in the sky like you see here, and some of you may have seen in person in a dark night sky, because we live within it. So we are inside this spiral galaxy, and the Milky Way that you see at night is the looking down that flat plane from within it, essentially. Now, this artist rendition is showing the Andromeda galaxy really close to us, because you may have heard that the Andromeda and the Milky Way are moving towards each other, and they will collide at some point. Now, breaking that down a little bit, there are some people who ask legitimately, well, if the universe is expanding, how are these galaxies going to collide with each other? And it's a great question. It just has to do with the scale. So the fact that overall you have our entire universe is expanding, but on local levels, you can still have these gravitational effects. So it's just how, close and far away and how big relatively we're talking about everything. Sometimes it's hard to wrap your mind around. So even though the universe is expanding, the Andromeda galaxy and the Milky Way galaxy are gravitationally bound to each other, so they will still be attracting each other. So question about dark matter, great question, if it has an influence on galaxies. And it does, and actually it's prevalent throughout even our own galaxy. The first detection of dark matter, and we'll come back to this when we talk about Hubble and how Hubble is used to detect dark matter, but the first sort of evidence that we had, I don't have the dates off the top of my head, but it was in the early 1900s that we were observing stars in our own Milky Way galaxy and trying to see how fast they were moving around the center. We knew that we were in a spiral galaxy, and we were trying to calculate how much stuff there is out there. And one of the ways that you can detect how much stuff there is out there is by tracking the motion of objects around the center. Think about it this way, right? We have our solar system. The sun is at the center of it, and the closer planets orbit it quickly. The further away you get, the longer it takes to go around. And we kind of know this intuitively, but it really does have to go to fundamental constructs of how gravity works. And by studying how far away something is and how quickly it's moving around the center, that can tell you how much mass is within it, how much mass it's orbiting. When they were studying the Milky Way galaxy, they were seeing that the stars on the outside of the Milky Way galaxy are booking it, basically. They're going a lot faster than we would expect it to be for how much we can actually see. Again, this is an artist rendition, but the Milky Way part, the big vertical stretch there, is a enhanced image of what we do see, and the darker parts isn't dark matter, it's just dust. Dark matter, we can't see at all. Again, I'll show a Hubble image in a little bit so we can talk a little bit more about dark matter. But dark matter is prevalent throughout. And so whether it is normal baryonic matter or whether it is dark matter, that still makes up the mass of the galaxy. And that's something that we can measure and is causing them to be attracted to each other because dark matter interacts gravitationally. So I hope that answered your question. Baryonic matter, thank you, is normal matter. Everything that we see, the periodic table is all baryonic matter. It just means that it's made up of baryons, which is like the way fundamental particles that make up atoms. So if you've heard of, protons, neutrons, any of those are all baryons fundamentally. So they make up every sort of atom that we see and touch and feel. And it's only 4% of our entire universe. So without giving everyone an existential crisis here, when I say the term baryonic matter, I mean stuff that we can touch and feel. The periodic table is all baryonic matter. Everything else is either dark matter or dark energy. And there are big question marks next to all of those. But we can see their influence on our universe. We just can't see it itself. So I hope that doesn't break too many brains, but stick with me. We're still gonna talk about dark matter a little bit more soon, but thank you for the clarification there. I appreciate it. So the question I specifically got was if the Andromeda galaxy and the Milky Way galaxy are moving towards each other, but we are seeing the Andromeda galaxy as it was because light takes time to reach us, right? Light is emitted, but it doesn't just instantaneously hit us. It takes time to travel and the speed of light. And because space is very big, by the time it reaches us, we are seeing it as it was when it emitted this light, not what it is now, because time has passed as that light was traveling to us. So we're kind of looking back in time. And the further away things are, the further back we're looking in time. Now, this is a hard concept to wrap your brain around. I thoroughly appreciate this. It's one of the hardest things to get used to when you're studying astronomy. The best way that's a little less existentially that you can use is to think about the fact that the sun is 8 light minutes away from us. So we're seeing the sun as it was 8 minutes ago. It has taken 8 minutes for the light to reach us. And then things that are further away take more time, so we see them older. Broad strokes. But the question is valid. So if Andromeda is moving towards us, but we're seeing it back in time, isn't it much closer? And hasn't it already collided with us? Again, I thoroughly appreciate this question, but it just has to do with numbers here. So the Andromeda galaxy is 2.5 million light years away. When we see a picture of it, which is enhanced and artificially made closer to us here, we are seeing that light. We're seeing the galaxy as it looked 2.5 million years ago. Not enough time has really passed that we would expect it to be vastly different. There will have been some stars that have gone supernova. So at some point there are bright flashes that will have already happened that we're still seeing the stars. The stars are currently no longer there because time has passed. But 2.5 million light years is not that big space-wise. When we talk about life cycles of stars and all of those, I'm sorry because I know people have bad memories with like scientific notation and things like that, but just remember billion and million, that's 3 zeros is the difference between those. And when we talk about the life of stars, like our star, the sun, its entire life is going to be 10 billion years. Plus or minus a few million, right? Because we don't know exactly. That's our error percentage on that. And so when we see the Andromeda galaxy, it is close enough to us on these scales that we're talking about that it's reasonable that this is still there. So we can calculate. It's actually a really hard calculation to do, where trying to figure out how close they are because the Andromeda Galaxy is so big and it's moving toward us so slowly that trying to figure out, okay, do we say the point closest to us? Do we say the middle one? All of this stuff is rotating. All these stars have their own motions as well, and it's slowly moving towards us. Trying to calculate exactly how is a bit rough, but the best estimate that we have so far is about 110 kilometers per second. So every second it's moving 110 kilometers closer to us. But space is very big and that's very slow. And that is comparable to how fast stars are orbiting the center of our own galaxy. So yeah, it's never going to be easy. Thanks a lot, space. but it is moving towards us. It's just trying to figure out exactly, and if we will collide or if we'll sort of graze past each other. But we do know that there is a gravitational attraction and that is happening because we see this Doppler shift that's happening from all of these stars. So cool stuff, really fascinating. But it's moving 110 kilometers per second. It's 2.5 million light years away. That means that it will collide in about 4.5 billion years, I think, ish. So it's going to be a long time. Yeah, I accidentally wrote down light years. It's not like it's going to be 4.5 billion years before it starts to kind of look like this. Before you look up in the night sky and this is what you see, it's going to be 4.5 billion years, at which point that's almost exactly when our star is supposed to die. So I hope we've colonized some other planets in the interim, but you get the idea. So it's a really good question. But again, we see the Andromeda Galaxy, it's actually not that much time has passed relative to space, that we're talking a whole other factor of 3 before they actually collide. So it's possible that, we just got the billion and the million mixed up because big numbers start to break our brain pretty quickly, and that's okay. Definitely understandable. Now, another one, we had Super DTG brought this up last week, so I have to talk about it, but that wasn't supposed to sound like I wasn't happy to talk about it because I am really excited to talk about it. But the supermassive black hole at the center of our galaxy. Yeah, whatever. I know you understand what I meant. But these, we've been tracking these stars around the center of our galaxy for a long time, and this is how we know that there is a supermassive black hole there, because we can, over decades, have looked at these stars and their motion, and in some cases have actually put together videos from these images that show stars approaching the center of this empty space at the center of our galaxy and then getting slingshot around, and then other ones come in and other ones come in. So again, I mentioned, like with a dark matter, you can see stuff orbit, and that tells you the mass of what's in the middle. If you can tell what's orbiting and how fast it's orbiting, you can learn something about how much mass there is in the center. That's the same thing we do with the center of the Milky Way galaxy. We do see that there is a lot of mass there, and there is indeed a supermassive black hole. But the big news that was a couple weeks ago that have to do with this is that one of the stars that we have been carefully observing here is precessing. So what do we mean by that? It's doing this. Now, this is an artist rendition. It's an extreme version, but this is really important for general relativity, which sounds fancy and scary and hard to do. But the general, I always call it general theory of general relativity. It's the general theory of relativity. Whatever, it's general relativity. This is what Einstein came up with. And this idea of precession was actually the first sort of thing that started to break Newton's theory of gravity, the one that we all have learned in science classes, and made us realize that that is a 99% solution and not entirely the physics that's going on here. Because, yeah, thanks. General relativity. So I'm allowed to call it whatever I want because I have a PhD in it. And yeah, I will pull that card. I don't pull it often, but I will pull it here. Now, the general relativity, what happened is that this orbit, this precession that we see, is what was observed with Mercury's orbit back in the late 1800s, early 1900s, and Newton's, even earlier than that, about mid 1800s, they were observing Mercury's orbit, and they saw that it precessed. It did this. And Newtonian gravity, the idea that gravity is a force, that two objects are attracted to each other, and it falls down as the square of the distance between them. So if it's twice as far away, it goes down by a factor of 4. If it's 3 times away, it goes down by a factor of 9. That works for most stuff, but it doesn't explain precession. If you took a star and a planet and they're orbiting each other, it should not precess like this if you're just using Newton's gravity, which is what we were using to describe gravity. That is what gravity was. So what they thought was, because astronomy is always this interplay between observation and theory, that you see a phenomenon and then you build the theories around it and then you try to confirm it, or you have a theory and then you're looking for this confirmation. It's always this back and forth because space is a big puzzle piece. We can't do a lot of this stuff in a lab. We have to rely on what space gives us to confirm or contradict our theories. And this broke everything. They thought that there could be a planet between Mercury and the sun that was tugging on Mercury to make this pattern. And but as telescopes got better and better, they realized we're not seeing it. They actually called it Planet Vulcan, which I love. There are old star charts from the mid 1800s that have Vulcan as a planet there. But telescopes got better, and we never saw Planet Vulcan until the 1960s in science fiction, in Star Trek. But that kind of caused us to really put a hole in Newtonian gravity. So Einstein started to think about gravity differently. This idea of a fabric of space-time had been around. It had been kind of proposed by mathematicians for a long time, and this idea that our universe is a four-dimensional fabric of space and time. What Einstein did is he said, what if we put a mass there? What if we put a bowling ball on the trampoline? What would that do? And as we've seen these gravitational wells that maybe you've played with at science museums, if you have this big mass in the center, you can get marbles to orbit it, and the further away they are, the longer it takes to go around. The close ones go faster, but you can actually get it to precess. You can get them to do this. And when Einstein applied, his equations for space-time with the presence of the sun and Mercury, indeed, you were able to see this precession build out. Now, that's awesome. That was sort of like the first, general relativity. That's looking good for gravity and physics. Yeah, score. And, touchdown. That's perfect. Now, he took a few days off. I would have taken longer. But what they recently observed, they just published that they are seeing that same phenomenon with a star around the center of our supermassive black hole in the center of our galaxy. So they have been able to observe a star, they call it S2, that they have been observing that is near the center of our galaxy, and it itself is precessing around the middle. So it's another thumbs up for general relativity. But because space is very big, the team that did this took 330 measurements of this star over the course of 27 years to see this precession happen. And they did see it. So now general relativity, we still call it a theory. With the discovery of gravitational waves, it's actually confirmed because we saw space-time itself moving from gravitational distortions. But it's always good to keep getting that confirmation. Astrophysicists have to be skeptical by nature because space can change anytime. So it would be mind-blowing. Now, it is, unfortunately, the center of our galaxy is 26,000 light years away. So that, even just in our own little home, is still, it's 26,000 light years away. So it would take 26,000 years to get there. So we are observing this behavior from 26,000 years ago, which is a few generations. So we'll have to protect some sort, or discover some sort of travel method to, yeah. Nice. All right, now we are going to transition start talking a little bit about Hubble. There was another news article that came out. Super DTG and Maggie Moo both sent it to me, so I want to thank them for doing that. But the disappearing planet. So this is something that hit the news this week as well. That has to do with a disappearing exoplanet. I've talked about exoplanets in the past. This is the first time here, welcome. Exoplanet just means a planet that is going around a star that's not our sun. So we have our solar system, we mean other star systems. When we observe other star systems with exoplanets, those are all within our own Milky Way galaxy. Just because they have to be really close, planets are really tiny in space. So those stars have to be pretty close to us for us to be able to see a star system. So by nature, any exoplanets that we see, we're seeing within our own Milky Way galaxy. Now this star, Fomalhaut, it's been a while since I took German. Apologies. Deep apologies. Is 25 light years away. And it was imaged by Hubble. This is a Hubble image that you're looking at. And they took observations between 2004 2006, which you can see here on the right. In 2008 is when they announced this. And so you can see this model, it says up at the top, the model of Fomalhaut B. They announced that this Fomalhaut B is a planet, as an exoplanet that's going around the star Fomalhaut. And it looks like a planet. But it had some weird characteristics. It didn't quite emit light in the same way that we would expect. Also, just a side note, but optical images of planets are incredibly rare. Most of the exoplanet discoveries that we have come from the Kepler telescope that was looking for dips in light curves from the star. So it's really just looking for the planet's shadow as it gets in front of the star. This is actually an image of the planet itself, which is rare in its own right. But you can see here that over repeated observations by Hubble, this planet seems to to disappear. And that's exactly what kind of hit the headlines was, a planet has disappeared. Well, we had declared it an exoplanet, even with like a little asterisk that said it's got some weird behavior. It's not emitting heat or light in the same way that we would expect it to be, but we're seeing this dense object orbiting a star. Now that they have these observations, and our observations continue to get better and are repeated, what this appears to be is actually we just caught this sweet spot around this star where we saw two icy comets collide. So when you look at this ring around the star on the left-hand side, that's basically a giant sort of asteroid comet belt, like a little bit like our Kuiper belts mixed with the Oort cloud. So there's a lot of icy chunks around this star. And these two objects, we think, the models match, are about 125 miles across, hit each other, went poof, big cloud of ice. But this cloud of ice was pretty dense after this first collision, and we just happened to take a picture then. And it was still pretty dense and close together the next couple years, but over time it started to fall apart. It's just, through melting, through dissipation, just all of this stuff. So it started to get away from each other. So some of that's optical phenomenon, because in order to see, that's a great question. So these rays pointing out why this image looks the way it does. The way we image stuff around stars, we have to cover up the star. And then we see the stuff around it. And then we sort of take that light away, and then we image the star itself. But in order to see the stuff around it, you have to cover it up because it's too bright. You can also think the analogy with that is like during an eclipse, where we have when the moon covers up our sun, we're able to see this halo around the sun that we wouldn't see normally because the star is too bright. And so here what you're seeing are more of like the physical rays themselves are more of just like the light rays that are coming off of the star when it's covered up, so we can actually image them. They're not structures that are physically laid out in beams like that. It's just this big cloud of ice essentially that's going around this star. Now the ring itself is a physical like it looks like a ring there. But what you're seeing there are the light rays hitting all of those ice particles, and ice is really reflective. So I hope that makes sense. But that's a really, really good question. Thank you for asking. So that was Fomalhaut B is no longer a thing. We went, oh, it's not an exoplanet. So, but still interesting. Space continues to puzzle us and be awesome. If there are no other questions from that, we'll carry on. And, oh, hey, welcome. Thank you for being here. So we're going to talk a little bit now about Hubble itself. And I'm really glad that you're here. So, this image was released today. Hubble, man. Hubble is amazing. For the last really 27 years, it's been sending out a lot of stuff. Exactly. It's been sending out some cool pictures. Now, I say 27 years because, the best desktop wallpapers. It's mind-blowing. Even if you haven't taken astronomy, if you have never, there's plenty of Zoom background. If you've never had the opportunity to take an astronomy class, welcome. That's why I'm here. But it's a lot of it is spent trying to wrap your head around the beauty and the awe and the sheer insignificance we are compared to space. Hubble can do that with one image, and that's just is so amazing about it. So this was released as part of this 30th anniversary. Now, Hubble was launched today, 30 years ago, on Discovery. Must say the USS Discovery. It's not Star Trek. On the Space Shuttle Discovery. And, but some of you may remember, some of you may not, there were some issues off the bat. So they got it up there, successful launch, woohoo! And then they turned the camera on and they went, ooh, that's not a great picture. And it was blurry. And what it turned out, yes, can we make that? That's our new headcanon, that Captain Pike is leading the Hubble maintenance mission. Yeah, let's do that. Basically what happened is the mirror, and there are a few astronomy people here in the chat with me, so feel free to jump in if I misspeak about something. But there was an aberration to the mirror, that it was not perfect. And in fact, it had a distortion that was only about 1/50th the size of a piece of paper, but it was enough to turn it blurry. It's that same thing of, like when you're in the optician's office. Optician? The glasses people, and they say, is it 1 or 2? Is it 1 or 2? And you're like, I can't tell the difference. But Hubble is so sensitive that you can tell the difference. Optometrist, thank you. This is why we keep you around. Yeah, see, we've just canoned that. So Pike fixed Hubble. That definitely happened. But they realized that there was a manufacturer distortion, an error. It was 1 part in 50, and it was a bit of a problem. Yeah, exactly. So it took 3 years to get back up there and repair it and install new cameras, and then lo and behold, almost 30 years of beautiful, stunning, mind-blowing pictures here. So what this is an image of is we have 2 basically nebulas that are going on here. And yeah, for space travel and space exploration, 3 years is a pretty quick mission to get something up there and cover it. Agree. This is not a Hubble image. This is a composite image. What we're looking at now. What I'm about to show you is not a Hubble image. But this is a sort of bigger picture that's really a feat in imaging of the Large Magellanic Cloud. So we'll go back to the Hubble image in a second, but the Large Magellanic Cloud, I've talked about before, but it's another galaxy that's in our galaxy cluster. And it's visible from the southern hemisphere. It's kind of cloudy cloud. But it's a cluster of stars. If you think about our Milky Way, the Large Magellanic Cloud kind of lives up here. Now, it has typically been referred to as an irregular galaxy, that it's not, doesn't have particular form. I've seen recent things that they're kind of redefining it to like a partial spiral, but galaxy classification is just kind of hard to wrap our heads around. And oh, you got to see it. So jealous. If anyone else here has seen the larger small Magellanic Cloud, I saw it before I was an astrophysics major, so I did not thoroughly appreciate it. That was the last time I was able to see it. Oh, wow. Yeah, that's a little bit mind-blowing. So great question. When we look at pictures like this, there is, to some extent, real color. Like, there are sort of colors in space from the images we get, but things like this are going to be slightly artificially enhanced. I can't speak specifically to what extent with each picture that we have, but what we do is, when we talk about astronomy and observations in space, space is, if something has elements in it, hydrogen is one of the most prevalent elements in our universe, in our galaxies and nebula. You're going to see a lot of hydrogen, and hydrogen itself is going to be emitting some sort of radiation. Other elements as well, other processes like stars exploding, stars forming, are all going to be giving off different types of signatures, like different heat signatures, and they'll emit in different wavelengths. Even within the optical wavelength, you're going to get things happening at different wavelengths. And so you take pictures of different parts in the spectrum, and then you color them slightly differently. So you enhance these different processes that are going on. So we talk about these as sort of optical images, but that they've been enhanced. And the way they're enhanced is you essentially can think about it maybe just taking like a red filter, a blue filter, a green filter, and then you lay it all on top of each other, and you can adjust the red, blue, and green enhancement. I think that makes sense. There's a lot. I mean, not even amateur astronomy, but professional astronomy, getting pictures like this, there's a lot that goes into it. But the nice thing is that when you do see images like the Hubble one I'll flip back to in a second, they do put a lot of detail in what they've enhanced and what those different colors mean. And typically it's associated with different elements where we say, for example, like chlorine, for example, is going to give off a certain signature. You're going to get maybe some ultraviolet light that we can't see with our eyes, but spill into that the telescope is sensitive to. We'll filter that as well. So thank you for the explanation. There's a lot to that, but all of these images that you see that are publicly released, especially scientific optical images, they will have detailed explanations that say, this is what this color is, this is what this color is. So definitely recommend you checking that out. But the reason I wanted to show you this image is because this is a huge project. This is this is a big imagery of the Large Magellanic Cloud. And it just is showing you that it's a really dispersed, there's lots of different clouds in here, that it's a lot of nebulae that are living in the Large Magellanic Cloud. So it's known for being like this, kind of wispy and cloudy. And the Hubble image that was released is from a part of the Large Magellanic Cloud. So, and I mean, the images are brilliant. That we see these in social media or put them on our desktop without a second thought, and that's okay. But we enhance different parts of these images that make them beautiful, and but there is science behind them. There's a reason that they look the way they do. We're seeing different processes that are happening that are colored differently. That just helps us study it a bit more. Now, this was released today, so haven't had a ton of time to dive into it, but it is 2 clusters. The big one, the big, shiny, beautiful, crazy one, is a star-forming nebula. So what's going on here is that there's a lot of hydrogen gas, a lot of dust. We're seeing a lot of heat from stars forming here. So we've talked a little bit about the solar life cycle, the star life cycle, but just to kind of briefly recap what happens, you have big clouds like this, big nebula, and what's going on is it starts to get close to each other, and you start to get these kind of clumping together. And when they start to clump, you start to have more gravity. And so more things are going to clump to it, and you're going to kind of clear out that area, right? That stuff, you get the snowball effect of dust and gas all kind of clumping together. As it's doing that, it's getting closer and it's heating up thanks to friction. It's heating up, it's starting to get more and more dense, and then eventually you get to this point where it's so hot and it's so dense that these hydrogen particles are so hot and close to each other, they fuse and they make helium. At that point, you have a star. Once you get this dense ball that is fusing hydrogen into helium, that's where we say it's gone from being a protostar, a pre-star, to being a star. And these star-forming regions are big clouds that have a lot of star formation going on inside of them. So that's this big one. The one on the bottom left is actually, I was kind of like, whoa, I guess like that. that was the one that I was really drawn to, because first of all, it's beautiful and we get this blue imagery, and but what actually is going on there is kind of mind-blowing. So this is, I think, I didn't write down, but NGC 2014 is the big star-forming nebula. The one on the bottom left is NGC 2020, appropriately, for lots of reasons. But yeah, NGC 2020. And this is actually a nebula that is surrounding a Wolf-Rayet star. So the star is named, just in a super easy to remember way, HD 269748 is the name of the star. But it's a Wolf-Rayet star, which basically means it's incredibly massive and bright. We talk about different types of stars. Our star is kind of an average star in the best way. It's special to us, but it's a fairly average star. You get these super massive stars. Wolf-Rayet stars put out a ton of energy. They're incredibly bright. So this star is over 60 times the mass of the sun, and it's shining more than 3 million times as bright as our star. More than 3 million times as bright this star is shining. And it's just giving off so much radiation that it's pushing out the cloud around it. So Wolf-Rayet stars are just so crazy that they shed their outer layers, that they're so bright. Stars have this balance of radiation and gravitation. You have radiation and gravitation. So what's happening is inside, when the hydrogen is fusing into helium, when that happens, it gives off light, or radiation is another word for that. Gives off this radiation. That radiation makes its way through the star and pushes out, but it's pushing out the star. What's keeping the star together is the gravitation, all of that mass there, that it's still really heavy, and so it's holding it together, and there's a balance between the radiation and the gravitation. Wolf-Rayet stars are so massive that radiation gravitation balance is a little bit screwed up, that these outer layers get shed off, and that it's being pushed out more than the mass can hold it back in. So it will supernova like nobody's business. Yes, absolutely. It will definitely supernova. It will probably be in a few million years, so it's hard to say, because again, our plus or minus a few million years is kind of hard for us with our generation. Our human life cycles don't really line up very well to space life cycles, but it will absolutely supernova, and it will be spectacular when it does. Now, again, it's not even within our own galaxy. It's in a galaxy within our own local cluster of galaxies called the Large Magellanic Cloud. It's actually 160,000 light years away, which is a good thing because it's very bright and it's giving off a lot of radiation. But one of the articles that Phil Plait wrote that I really appreciated from this was the fact that, like, the nebulas that we're looking at here, one is this big star forming region, that other one that has lots of stars in it, hundreds of thousands of stars in it, hundreds or thousands of stars in it. The one down below, all that radiation is coming from one single star that's illuminating all of the gas around it. So again, take everything I'm saying with a little bit of a grain of salt, because this image has not been out that long, so I haven't had as much time to digest all of it, but that's kind of the first rundown that we get with it. And this is going to be my background for a little while, because it's beautiful. And yeah, so I hope you enjoyed that. Let's look at some of the other stuff that Hubble has given us over the last 30 years. I think it's, without saying that there's been some amazing stuff, but some of the science that we're able to do. So the deep field. This is hard. This is what breaks a lot of people. Stick with me as long as you can. If you need to go cry afterwards, if it's beer o'clock when I'm done, then I respect that. If it's beer o'clock now, then hopefully that helps. But the Hubble deep field, I believe it points toward, and correct me anyone here if I'm wrong, but Ursa Major, in the direction of Ursa Major, that especially to the naked eye, but even, decent telescopes, is a fairly dark part. There's not a lot of stars there within our own galaxy. So it's kind of just a little bit of an absence of stars. Not anything weird, no weird phenomenon, but there's not much blocking our path, so we can see out of our galaxy there. And when we see out of our galaxy, we don't really see anything. And Hubble points towards this dark spot, opens its aperture, and says, "Light, come to me." And all of this light, it's essentially just long exposure of single photons that are building up, that have traveled millions and millions and millions of light years through the universe, reached us. And what we're looking at here are galaxies, not stars. Talked about our Milky Way galaxy, hundreds of billions of stars in it. It's big and hard to wrap our mind around. We were talking earlier about the Andromeda galaxy and how far away it is and how slowly it's moving, how big space is, that we can only see exoplanets just within our local area of our own local galaxy. These are galaxies. Like some of them you can kind of tell because you can see them being, you can see the spiral galaxies there. There's sort of a nice pretty one on the far, about midway down, far left side. You can see these flat angles. Hubble Ultra Deep Fields, look up these pictures. It's taken a few of them. It's composited over the last 25, 30 years of taking these pictures, and it is hard to wrap your mind around that every single one of those dots is hundreds of billions of stars, and how far away they are. It's just existentially difficult and beautiful, but difficult to wrap our heads around any number of that. One of the things, other than giving us massive existential crises, one of the great things that we can do with this, though, is there's a lot of science that we can pull from this. Thank you. I'm glad you appreciate that. Yeah. That's a great image. Yeah, exactly. Just let's have a little bit of a mind blow here. So let's take a step back from the existential crisis. Look at the science that we can get from this. One of those things is gravitational lensing, which as a gravitational astrophysicist, I have to talk about and geek out about all the time. But we can do gravitational lensing. So the way this works is you have light from a distant galaxy, you have a big cluster of galaxies or a big cluster of mass in the middle, and then we're over here. As that light starts to come towards us, it gets bent around that. If you're having a hard time imaging that, think about that bowling ball on the trampoline again. Flicking a marble so it grazes past the bowling ball, it's going to curve. And someone on the other side of that trampoline will see it coming from a different direction than from the direction you sent it. So this gravitational lensing happens on all different scales of gravity, between like just our sun lensing starlight as it goes past it, all the way to galaxy clusters lensing massive galaxies behind them. But this is an image that shows this. Now, what's highlighted here is you have those red circles. Those are all the same galaxy. Now, we have a galaxy cluster in the middle. That one galaxy, this is the orange one, is the light is getting lensed around, so it travels this way and then it comes here. So here we're observing it and it appears to be coming from this direction. The light is also being sent, it's being sent off from this galaxy. It's being sent here and it lenses, and there's another copy of the image appears to be coming from this direction. So we get all of these different images of the same thing that's being lensed around the center. The same thing with a quasar. So quasar is a really bright signal that's coming from, we suspect, the super black holes at the center of galaxies, getting these bright flashes coming for it. And because it's kind of a hard sell to tell you that it's the same thing, because you can't just be like, oh, they're all blue and bright, so that's the same thing. There is more science that goes into it, that you can actually have the spectrum, that you see the signal coming at different points, and you can see that it's the exact same spectrum. So that's how you know it's the same thing. So question here about why our galaxy doesn't have a quasar. That's a good question. I think that's something we're trying to figure out. I think it just has to do with masses and ages of the galaxy and what's near to it and what's not. But I think that's an ongoing question in astrophysics, is how often do supermassive black holes in the center of galaxies results in quasars, and what exactly is causing them to happen. We can file quasars away to talk about future episodes, because I'd like to dig into it a little bit more so I can give you a better explanation as well, but it's a good question, and continue to discuss. So it is filed away for future. We will talk about quasars. So yeah, we see this lensing, but one of the things that it gives us, so when I was talking about dark matter, there's a question earlier about dark matter in galaxies, we talked about how you can measure orbits around the center, around a mass, and from that orbit, you can learn about how much mass is there. And that was the first indication of dark matter, that there's a lot more mass in our galaxy than what we can see. Gravitational lensing, what we're seeing here, is a similar way to detect how much stuff is in the middle. If we have these distant galaxies that we can take pictures of, and the light is being lensed by this cluster in the middle, by the time it reaches us, how much it's been lensed can tell us a little bit about how much mass there is, how much stuff there is in the middle. And this is another way that we've used to measure dark matter, and the dispersion of dark matter particularly. Lots of combination studies done between Hubble and the Chandra telescope, an X-ray telescope, where they image collided clusters, so galaxy clusters that appear to be either close to each other or just past each other or have merged, using gravitational lensing and using X-ray observations. The X-rays tell us how much baryonic matter, how much hydrogen, helium, stuff that we know made up of atoms is there. And the gravitational lensing can tell us how much stuff is there that we can't see, that isn't emitting any light. For those of you Star Trek fans here that may have found me because of Star Trek, you know you're always welcome. And anyway, it's cloaked Klingon ships is the way I like to think about it. If you think about or Romulan ships, pick your poison. But if you think about cloaked ships in science fiction, they're not emitting any light, right? That's the idea, that you can't see them at all. But they still have a gravitational presence. Valid. They still have a gravitational presence. And so, in theory, you could detect the presence of a cloaked ship by light being curved around it. And indeed, this is one of my favorite things that they did in Star Trek Discovery, is that Tilly, that's exactly what she did to detect cloaked Klingon ships, was use microgravitational lensing, tiny curvatures from light. As you jumped around this empty space, you can map the background stars and see how light is being distorted from those. So you would have to jump around them hundreds of times, which is what they do. I think the number is like 133. There's no scientific reason why it has to be 133, but you would have to jump around them a lot. Particularly the galaxy in this image that I'm excited about right now. That's a really good question. This image, they're all mind-blowing because it's hard to, even you just pick a dot and then you look at it and you realize it's a whole galaxy. And that's so existentially difficult. And there's so much. I mean, I'm a sucker for like the really clear established spiral galaxies. Oh, I didn't have a picture of it and I was kind of sad I didn't, but I realized I have it tattooed on my arm. But this is this is a galaxy cluster that they artificially I can't believe I'm doing this. They artificially colored the actual matter pink, and then the blue stuff on the outside that's extended beyond it is the stuff that we've seen gravitational lensing that indicates that there's dark matter. Not just that there's dark matter there, but that the dark matter just passed right through, that it didn't collide in the same way normal matter, baryonic matter that we know does. Tattoos for the win. And so that's obviously one of my favorite images of all time. But I did put my favorite Hubble image here for your viewing pleasure that we can end on. Even though they're giving me a run for their money with the one that was released today. But mine is a gravitational lensing image of a smiley face in space. So this is, again, gravitational lensing. What you're seeing there, what's making the smiley face, is spiral galaxies that are being curved around. Now, if a galaxy is perfectly aligned, it's going to make almost a full circle. But rarely in space is it so perfectly aligned that you get a full circle. But this is pretty darn close to it. And, if you search for Einstein crosses, that's sort of the most common ones where, let's just pretend we're going this way. So there's an object back here. If it's perfectly aligned, it's going to be a perfect circle. But if it's off by a little bit, you're still going to get multiple images, and sometimes it forms a cross. So that's Einstein crosses. You can look up more pictures of those if you're so inclined to see that gravitational lensing. But we have to end with a smiley face in space because it's my favorite one. All right. With that, we are pretty much at the hour. If there are any last questions, the Kool-Aid Man, I'll haunt your dreams. Always loved, is the Kool-Aid Man the Kool-Aid or the pitcher? So I've given you enough crises to deal with in one day, but we love it. Oh, hi! All right, awesome. And we have a vote for the pitcher, so we'll end it on that. But I love you. I love you all. Thank you so much for hanging out with me. I really appreciate you spending your Friday afternoon, evening, morning, whatever time it is for you here. And we're ending on that image of Kool-Aid's juicy organs. It's how we roll. All right. Well, thank you again. I really appreciate you being here. And I hope to see you again. We will be doing our Star Trek brunch on Sunday. We have a very special guest who will be joining us. We're talking about Redemption and Darmok on Sunday morning. And then for our episode club on Tuesday, we are going to be discussing science in Avengers Endgame. So be sure to come and join us for that. We have social media links down below. If you're one of the patrons, you can vote on episodes that are coming up. And I'm really excited to see you all there. Thank you for spending time with me. Take care of yourselves. Take care of each other. Get up, stretch, have a glass of water. I love you. Space rules at Astra. Until next time. Thank you.